Our last topic for this unit is energy and capacitors, which you're going to be learning today. It's not a whole lot mathematically. I'm just going to give you some formulas, not even going to do the derivations, but there is kind of a weird concept, and we'll get into that in a minute. First up is the energy stored inside a capacitor. So the whole goal of a capacitor is storing charge, and when you store charge in a manner that separates positive from negative, that creates a potential difference. And if you create a potential difference, then you have energy stored. So that's what a charged capacitor does, is it stores energy. And that's electric potential energy given by the equation here. That's U for potential energy. And it's equal to both of these different things. These are equivalent. You can work that out if you want to. You don't have to. Q is charge, C is capacitance, delta V is the voltage across a capacitor. Something you might note if you're familiar with other energy equations in physics is that this looks like an energy equation for lots of other things. You've got Hooke's law, which says the potential energy of a spring is 1/2 kx squared. And then also the kinetic energy of a system is 1/2 mv squared. So it follows that same format. You've got 1/2 times some property of the system. For capacitor, it's the capacitance, and then times something squared. And really the reason these all look the same is not because of some phenomenon in physics. It's because of the way calculus works. And if you want to get into that, you can ask me, or you can take a a calculus-based physics class, and you'll learn all about it. So that equation told us how to calculate the energy stored in a capacitor or a system made up of two equally and oppositely charged things. Now, here's the weird concept. The concept is that the potential energy is stored between the plates in the electric field. So up until now, we've treated fields kind of as this mystical mathematical quantity that exists and it causes forces, but it's not there per se. It's not something that you perceive. But the weird thing is that the energy stored in a system that's electrical is held within the field itself. It's not in the plates. It's not in the charges in the plates. It's in the field itself, which is a super weird concept. And the title of the slide says, "Don't ask why, you'll get the Feynman answer." And that's because there's really not a good explanation why. If you watched the Feynman video from the first day of school, where somebody asks him why two magnets attract or repel, and he goes off into this long spiel that's a little bit facetious that says, well, why is not a question that we can answer indefinitely. At some point, you've got to just accept something as true. This is going to be one of those things that you need to just accept as true. But to think about it in a little bit more concrete terms, we're going to talk about springs very briefly. So a spring gets stretched, like you can see in this stock photo that I stole from the internet. When you stretch a spring, that stores some energy. And if you hold that spring stretched, you're doing work, and that spring, if released, will produce kinetic energy. So that is some potential energy stored in the spring. Now, that energy is not stored just in the ends of the hooks that you're pulling on. It gets stored all throughout the coils as well. That's kind of vaguely the same idea as a capacitor. It's not like you can take a capacitor, stretch it, and make more energy. That's not what I'm saying. What I am saying is that the energy isn't just stored in the ends, it's stored in the middle where the electric field is. The electric field is analogous to the coils on the spring here. And this seems super abstract, and it is super abstract, but there is a daily phenomenon that you experience. Well, you might not be experiencing it since you're staying at home in the indoors all the time as a virtual student, but there is a phenomenon that we experience all the time that will kind of help put this in concrete terms. That more concrete example that we're going to look at is light. So the wave-particle duality says that light can be both a particle and a wave, which is true in a weird sense. We'll get into that in December. For today, we're going to treat it like an oscillating set of electric and magnetic fields, which is what light is. It's just electric and magnetic fields propelling each other. The electric field will push the magnetic field, which will push the electric field again, which will push the magnetic field again. It'll just keep going forever, light propagating on indefinitely at the speed of light. It's pretty cool. We'll look at it later. But the main thing to take away is that light is made up of just fields. Fields alone. It's not particles with charge, it's not particles with mass, it's just field. Okay? Fields moving through space. But when light hits you, like light from the sun, your skin warms up. And that's because the molecules in your skin are absorbing energy from that light, which is jiggling the atoms, making the temperature of your skin rise. So the fields that make up light were carrying that energy from the sun to your skin. The energy is held itself within the fields, which is super weird. We also see this in dealing with electrons. So in the Bohr model of the atom, you have electrons that are going in orbits around a nucleus. It's my little nucleus. Here's a ring. You probably know by now that the rings don't actually look like rings. They look like crazy three-dimensional things. But we're going to pretend they're rings. And electrons can absorb light. So if light hits the electron, it can absorb it if it's the exact right energy and jump up into a higher energy state. It absorbs that energy. Or it can jump down to the lower ring and it's going to release energy. And that's because the light, the electromagnetic waves, can store that energy and move it somewhere else. So it's a weird concept that the energy inside a capacitor is held entirely within the field. But we can see using light that that is possible. And I'm going to throw a slide after this that is a bunch of words. And really, it's not something I'm going to talk all the way through. You can pause it and you can read it, or you can look it up in the slides in Google Classroom. It's some good information. But it's basically the same stuff I've just covered here. In dealing with this energy that's stored in the fields, it seems a little crazy, seems hard to conceptualize, and the best explanation that I've found for it is that energy stored in fields is the total energy required to assemble the fields all together. So in a capacitor, you have to move all of the charges onto these two plates, which are separated by some distance d. Now when you assemble a bunch of charges that are oppositely charged, they're going to pull on each other, but to maintain that distance, it requires a certain amount of work, a certain amount of energy, and that is the energy that gets stored in the field. The total energy required to make that field possible is equal to the amount of energy that's stored inside the field itself, and this makes sense due to conservation of energy. The other thing you're going to have to know how to calculate is the energy density. So energy density in a parallel plate capacitor is defined as the energy stored divided by the volume of the whole field in which it is stored. So in a parallel plate capacitor, which I will draw here not with a highlighter but with the pen, there we go. In a parallel plate capacitor, we're going to put positive charges on this side, negative charges on that side. You've got a field permeating this whole space inside the capacitor. And these plates, they have an area and they're separated by some distance d. So the energy that's stored in this electric field, given by the previous equation, U of the field equals 1/2 times capacitance times delta V squared, gets divided by the volume in which the field is stored. So the volume the field is stored in is the volume inside the capacitor, which is simply the area times the distance. Now I know exactly what we needed was another variable that has V as its symbol. This V right here is volume. I'm using that for volume. I'm really not going to use it anywhere else. Everywhere else I'm just going to use AD for volume inside the capacitor. Now the energy stored in a parallel plate capacitor is given by this equation. To find the energy density, you take that energy and divide it by the volume in which it is stored, AD. Now if you want to do a bunch of algebra, you can take this idea and you can, using other definitions and formulas, get around to this equation, which is 1/2 dielectric constant times epsilon naught times the magnitude of the field inside the capacitor squared. I'm not going to do that here. It's a lot of algebra and it'll probably confuse you, and I don't want to deal with it. So if you want to try it on your own, you're welcome to. You can send it to me. If you want me to send it to you, I've got it written out on a piece of paper and you can have it. But I'm not going to do that derivation here. But the energy density, which is this little u, energy is the capital U, energy density is the lowercase u, is equal to 1/2 dielectric constant times permittivity, free space, times the magnitude of the electric field squared. You will have to use this equation on one of your homework problems, and it's not really written anywhere else, so this is where you find it. Now we're going to put all of that together and solve this lovely problem. The lovely problem says a portable defibrillator, can't say words today, defibrillator unit contains a 150 microfarad capacitor that is charged to 2000 volts. So side note, a defibrillator is, the thing they shock your heart with, like an AED, automatic something defibrillator. Anyway, AEDs. And they contain a capacitor inside them, and that's what provides the shock. So they will connect the capacitor to a battery, and it'll charge up. The charge will run to the sides of the plates, and it'll have some potential difference, and they shock your heart with it. They ground the capacitor to your heart, shocks the heart, hopefully makes it work correctly again. Anyways, so that's what happens with defibrillators. This defibrillator has a capacitor that has a capacitance of 150 microfarads, and the battery charges it to 2000 volts. And we've got a couple of other things that we know about the capacitor here. Capacitor plates are separated by a 0.01 millimeter thick dielectric with a dielectric constant of 300, which is a rather large dielectric constant. And we've got two questions. The first one is, what is the energy density in the electric field when the capacitor is charged? And the second one is, how much total energy is stored in the capacitor? And actually, I flipped these in class. I don't know why the book where I draw these examples from put them in this order. It's going to be easier if we do B first and then A, because we have to use the answer to B in A. So, first question I'm going to answer is, how much total energy is stored in the capacitor? And that equation is right there. I keep accidentally using the highlighter tool instead of the pen tool, and then I have to undo it, and you don't even see it. You just see me flustered for 30 seconds. Sorry. So first thing we're going to do is find the total energy stored in the capacitor using that equation. The equation is 1/2 times the capacitance times delta V squared. Cool, we have all of those things, and this is equal to the total energy, capital U. I'm going to make my capital U's like that so that they look more capital. This 150 microfarads is the capacitance. Micro is 10 to the negative 6. So we get capital U equals 1/2 times 150 micro is times 10 to the negative 6 farads. And delta V is 2000 volts. And that delta V is squared. So we're going to type that into handy dandy calculator, and you get 300 joules. Joules is the unit of energy for your total energy that is stored inside the capacitor. That's really just plug and play. It's not difficult at all. You just gotta take the numbers, plug them into the formula. But question A, what is the energy density, gets a little bit more difficult. Energy density is defined as the energy stored, which we already found. I'm going to highlight it in green. We already found the energy density, and you have to divide it by the volume in which it is stored, which is the volume of the capacitor. And for a parallel plate capacitor, the volume equals the area of the plates times the distance between the plates. Problem is, we don't quite have the area, but we can use another formula to calculate it. The formula for capacitance in a parallel plate capacitor equals dielectric constant K, or kappa, times epsilon naught times the area divided by the distance. We have all of these values except the area, which is what we're looking for. Capacitance is 150 times 10 to the negative 6th farads, which is equal to the dielectric constant, a given, 300 times epsilon naught, the permittivity of free space, which is a constant, 8.85 times 10 to the negative 12th with some unit that I'm not going to go look up right now, times A, which is what we're looking for, divided by the distance between the plates, and that's given as 0.01 millimeters, which is times 10 to the negative 3rd meters. And we can do some algebra to figure out what A is. When you do that algebra, you should get that the area of the plates equals 0.565 meters squared. That's the area of the plates. So now to find volume, you're going to multiply that area times the distance between the plates, A times D. So 0.565 times 0.010 times 10 to the negative 3rd gives you a volume of 5.65 times 10 to the negative 6 meters cubed. That is the volume. So now to find the energy density, you're just going to take the energy, 300 joules. Sorry, I'm writing in the wrong color, and you're not going to see it because I'm hitting undo. Okay, 300 joules divided by the volume, which was 5.65 times 10 to the negative 6 meters cubed. So your energy density is going to be 300 divided by that, which is, I'm going to make all of this smaller. Things are moving in weird ways. It's fine. Your final answer is 5.31 times 10 to the 7th. And that's joules per meter cubed. The energy density in that defibrillator. And that's all we have for today, just finding energy in the capacitor, energy density in the capacitor. There is one question in your homework that's a little bit odd. It asks about comparing energy density of a capacitor to the battery in a truck, and the energy density given for the truck is in joules per kilogram because it's looking at the energy to mass ratio. So on that question, you're not going to do energy to volume, you're going to do energy to mass. It's a little bit different. Don't freak out when you get there. But that's about it. All right, this is the last topic before your test. So make sure you finish your homework, kind of know what you're doing. Email me any questions. Tomorrow will be review and a little bit of practice, and then Friday will be the test. You will have to take the test during your scheduled class time, which is second block, which starts at 9:27. So be ready.